Alright, in this video we're going to talk about chemical formulas. We're going to talk about some of the different models that we use to represent compounds, and I'm also going to briefly discuss isomers. So the easiest way to represent a molecule is to use the molecular formula. In the molecular formulas, we represent a molecule or compound by using chemical symbols to indicate each type of atom that's present, and then we use a subscript after the symbol to indicate the number of each of those atoms of that particular element in the molecule. Now, by convention, we only use subscripts if there's more than one atom for that particular element. So in this case, this is the molecular formula for ethanol. There's only one oxygen in ethanol, so we just write O. So if you just see an atom with no subscript, the 1 is understood. Now, a structural formula shows some of the same information as the molecular formula, but we also indicate how the atoms are connected. So if this is the molecular formula for ethanol, this would be the structural formula. And so we actually show how all of the atoms are connected. And the structural formula gives us a lot more information because, as we'll talk about a lot this semester, we'll talk about it a whole lot in 1212, and then much of organic chemistry depends on this. The properties of molecules depend not only on what atoms are present, but how they're connected to one another and what the shapes of those molecules are. So the structural information gives us a lot more information because we can see how things are connected. Now, if we wanted to know what molecules actually look like, the structural formula is better because it tells us how the atoms are connected. But it doesn't really tell us the shape of the molecules. And so very often you'll see us use ball and stick formulas. And so these are all for the same molecule. This is all for C3H8. This is propane. If you have gas grills, the fuel that you use is most likely propane. A ball and stick model, this is the ball and stick model for propane. This gives us even more information than the structural formula, because now we can see, right, the 3 carbons don't make a straight chain, right? It's actually bent. And so we get more information about the shape of the molecule in these ball and stick models than we do from these more simple structural formulas. And if we wanted to know what propane actually looked like, sometimes you'll see these space-filling models. And so this is probably the most accurate representation. If we could actually see molecules, this is probably most closely what they would look like. The reason we still use the ball and sticks is because it's sometimes hard to see exactly what the shapes are in here. The blobs are so big, it's hard to see exactly what the atoms are, how they're connected, and what the shapes are. And so, while this is probably a more accurate representation, it's easier to see what's going on in these ball and stick models. Now, if we go back to thinking about elements, many elements do exist as discrete individual atoms. But some elements actually exist as molecules. And so there are 7 that exist as diatomic molecules that we actually need to know because they're so important. They come up so often in chemistry. So when we find hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine in nature, or in the lab for that matter, we don't find individual hydrogen and nitrogen and oxygen atoms. In a sample of hydrogen, we always have 2 atoms of hydrogen connected together into a hydrogen molecule. And so when we represent elemental hydrogen, we represent it as H2 as a molecule. And just a note on nomenclature here, if you just write H, that indicates 1 hydrogen atom. If you were to write 2H with 2 out in front, that would indicate 2 separate hydrogen atoms, whereas H2, now you're telling me it's a molecule. So now we have 2 hydrogen atoms connected together. Or 2H2 would indicate I have 2 hydrogen molecules. Now, it may be easy enough to remember these, but if we look at the periodic table, right, the elements that exist as diatomic atoms are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So I think it's pretty easy to remember that our diatomic elements are hydrogen, nitrogen, oxygen, and the halogens. Or another trick, there are 7 of these guys, right? And if we were to go like that, that kind of looks like a 7. So that's one way to help remember our 7 elements that exist as diatomic molecules. Now, those 7 exist as diatomic molecules, some elements exist as even bigger molecules. And now you don't have to remember this one. I just wanted to use it as an example. The most common form of elemental sulfur is actually S8. And so these are the structural formulas and then the ball and stick and space filling model of an S8 molecule. All right, another really important thing I need to mention when we're talking about molecular formulas is the difference between empirical formulas and molecular formulas. And so a molecular formula tells us exactly how many atoms of each element are present in that compound. An empirical formula just tells us the simplest whole number ratio of the number of atoms or ions that are in that compound. And so the empirical formulas have less information than the molecular formulas. But sometimes that's all the information we have. Like if we have an unknown compound, it's generally easier to find the empirical formula than it is to determine the molecular formula. Or we do have ways of doing that. And so just as an example, I have a ball and stick figure and a structural formula of oxalic acid. And if we wanted to write down the molecular formula, I would count up the atoms of each type. So I have 1, 2 carbons. So it would be, the molecular formula would be C2. I have 2 hydrogens, so we'll say H2O4. That would be the molecular formula. Now the empirical formula is the simplest whole number ratio. So since all of those are divisible by 2, and divide all those by 2, I would get CHO2 as the empirical formula. All right, and the final thing I wanted to mention was isomers. So we've used ethanol as an example before in this video. Ethanol has the molecular formula C2H6O. And this is a ball and stick figure of ethanol, but this is not the only way to connect 2 carbons, 6 hydrogens, and an oxygen. And generally, especially as we get to larger molecular formulas, there are generally lots of different ways to connect these atoms together. And if the atoms are connected together differently, we get different compounds with different properties. And so isomers are compounds that have the same chemical formula, but different molecular structures. And because they have different molecular structures, because they have different shapes, they are different compounds, and they have different properties, sometimes very different properties. And so just in this simple example, 2 isomers that both have the molecular formula C2H6O are ethanol, and then this is dimethyl ether. You can see in ethanol, the 2 carbons are connected together. In the case of dimethyl ether, each carbon is connected to that oxygen atom. And just a simple example of different properties, although there are a lot of other properties that are different, the boiling point of ethanol is 78 degrees Celsius, whereas the boiling point of dimethyl ether is negative 24 degrees Celsius. So at room temperature, ethanol is a liquid and dimethyl ether is a gas, among their other differences.